As you're playing a flute, you wonder about all of the different notes and pitches that you're playing, and you make the realization that your flute is playing at different frequencies. Now, because you are an astute physicist, you wonder what are the possible frequencies, what are the possible notes that you could play on this flute. So this flute is an open tube, meaning over here we have just an opening. And if we have a standing wave, if we've created a frequency at which our waves interfere with one another, then there must be an antinode at each open end. So let's consider what this looks like. This standing wave bit is, well, how long of a wavelength is that? If this is my total wavelength, that must be 1/2 of a wavelength. So let me erase this because it's not actually in the tube. I could say that this whole gap is 1/2 of a wavelength, which is the distance of the tube. So that's equal to L. That's the fundamental frequency. I can't get any lower than that. There's no possible combinations of waves to have two antinodes at the end. And you should be familiar at this point how to turn this wavelength into a frequency. I need to express it by the speed of the wave. So my velocity, let's assume this is in air, so the velocity of a wave in air is equal to the wavelength times the frequency. Rearranged for the frequency, it looks like that. And I could say that my wavelength, rearranging that equation, is 2L. So for a fundamental frequency, it's dependent on the speed of sound over how long this flute is by 2. That is the most basic, most fundamental frequency that the flute can achieve. Now, the flutist speeds up the air moving through the tube, creating, let's say, the second scenario. Well, how many wavelengths is this? I see one full wavelength since it starts at the bottom of the wave and then reaches that same bottom. This must be one wavelength. It's over the span of the tube, L. And I'm going to do the same process to try and express this by frequency. I have my wavelength, I can plug that in, and so the frequency that I must be playing at here is F is V over L. And I'll do it one more time to try and pick out the pattern. This must be, well, I see one wavelength, there's a half wavelength, so that must mean that there is a wavelength and a half across the tube. Rearrange this for lambda, you get this expression, you can plug it in to your relationship and get the frequency is 3V over 2L. Well, what's the pattern here? I see a V over 2L in every one except for this one. Maybe it is there, maybe we could say this is V over 2L and that the integer there is 2, and that would cancel, the 2's would cancel out. So I think the pattern here is the frequency is n V over 2L, where n is some integer based on how many, what the wavelength is that you have in any given scenario. So this looks very similar to, I'll box this, because this is important for open tubes. This looks very similar to the resonant frequencies that we got when we derived the frequency for a fixed string. But instead of displacement, so this spring was moving up and down, we could say, let me go grab that real quick. We could say that the spring was displaced. Now, instead of displacement, the waves are measuring air pressure change. So, where's my red marker? There we go. If I'm modeling this situation up here, I could say that these are the antinodes. This is where the air pressure will change. At the node, the air pressure is going to remain the same during this entire standing wave. So if these are the air molecules, the density of these air molecules will stay the same, and maybe the wave travels this way, and it's a place of low density, and all of the there's much more density over on the other end. And a moment later, now there's less density here, and now there's greater density on this end. So instead of displacement, we are measuring the change in air pressure from location to location, where the node is a place of constant air pressure. All right, we are going to move right along to closed tubes in the next video. Stay tuned.